So who am I? I'm Adrian Kaler. I have many hats, but I am a startup founder. I am also the founder of the Silicon Valley Deep Learning Group, which is sort of another gathering that I know some of you have come to and I recognize you from. It's nice to see the same faces again, and hopefully some of you who are meeting me for the first time will come to that group. Of course, I don't talk a lot at that group. I mostly run around and set up the video recorder. So we have lots of good speakers there as well. So hopefully you'll come and join us. And hopefully folks from our group will discover this meetup as well and come and join you. So let me give you an idea what I'm going to talk about tonight. So I like sort of technically meaty talks. So I tried to make this talk reasonably technically meaty. But I also like talks that are compact and to the point. This talk might be less of that because I had so many things I wanted to try to introduce that maybe it got a little long. So if I talk a little fast, it's only because I'm afraid of running out of time. What I'm going to talk about, what is the point of all this? Okay, so this is meant to be a technical talk, right? It's meant to be informative to people who are at various levels in the field. If you have no idea what a key point is, never done computer vision, anything like that, I hope that you get something out of maybe 25 to 30% of the slides. If you're a deep expert in this topic, you may get very little out of this talk unless you find that my presentation of it is somehow pedagogically superior to yours and you want to steal some of my jokes or whatever. But if you're anywhere in between, I hope that most of the talk will be interesting to you, okay? So this is really, I have in mind people who are very new to the field of computer vision up through people who are kind of intermediate practitioners who may not think about this particular subtopic so much. There's lots of things I could cover. I will not cover all of it. Most importantly, I will cover the shameless plug for my book. So this, as any author will do, okay? I even have a copy here that I can wave around, and I can use it for self-defense because it's like 1,000 pages. So this book here it's follow-on to the 2008 book, which some of you may have. That book, Learning OpenCV, was really good in helping everybody kind of get on the board with OpenCV. For a long time, the documentation was just terrifying. And Gary Bradsky and I, Gary was the original creator of OpenCV, sat down one day and said, we got to do this right. And so we started writing documentation. We said, why are we going to write this documentation for free? Why don't we write a book and get paid for it? Then we decided to go with O'Reilly, which is fantastic for outreach, maybe not as good for royalties, so it was a compromise.
Kindle edition for this book?
Huh?
Amazon Kindle?
Yes, and I'm going to recommend that you buy it because this book is now over 1,000 pages. It's really thick, it's heavy, it will hurt your back, okay? So I really recommend going electronic. It costs you less, costs O'Reilly less, it's better for everybody, and it's a lot easier to manage the size of the document. Originally, they were giving us a lot of pressure to keep it down to the size of the old book. We said, hey, this is the electronic era. We'd rather give people more and just let them put it on their Kindle or whatever. So that's what we did. So, okay, I'll stop plugging my book, except I will add this one thing. This talk is largely drawn from chapter 16 of the book. So the book has a lot of material in it that wasn't in the previous book. In addition to going to C++ and just sort of general updating relative to the library, there's a lot of new material, things that have happened in the field in the last 10 years. So key points and key point techniques are a big part of it. So chapter 16, most of the stuff in this talk is a summarization or relates to material in chapter 16. So if you want to go home and do the homework is read chapter 16 and do the exercises at the end. I will speed up. There are a lot of foils. So what are we going to cover? I'm going to give you a brief introduction to OpenCV itself. Someone asked, what's OpenCV? So if you don't know, I'll give you a very, very brief introduction. Then I'll talk a little bit about key points in a very abstract form. Like what are these things? What is this technique that people use? And then I'll talk about descriptors, which is kind of part of how you use the key points. And then a little bit about various kind of applications, key point matching, object recognition, and so on. Those things, the applications, I'll talk about kind of briefly at the end, but hopefully it will give me an opportunity to kind of take all the more technical stuff we've done on just what are key points and then show you how they can be applied. So a little bit about OpenCV. What's OpenCV? OpenCV is an open source computer vision library. It was started back in the before time, in 1999. It came out of Intel. And originally the idea was, people need to buy faster computers and nobody could figure out what those faster computers would do. So they sponsored a lot of projects to kind of, consume compute power. And OpenCV was born there. It matured there under Gary Bradsky, who I mentioned earlier. And in 2006, it kind of graduated. At that time, open source was very trendy. OpenCV was released from inside of Intel and became basically part of the community. It's under an MIT license, which is like the most permissive license you can imagine, right? You can basically do anything except claim to own it yourself. You can use it in your projects, you can modify it, you can do anything you want. You don't have to contribute stuff back, though we hope that you will. The open source community around OpenCV is extremely large, 13 million or more downloads, 7,500 forks, 4,100 patches in the last 6 years that have been merged back in, right? So it's all maintained on GitHub now, and you yourself could become part of the OpenCV development community, and I hope that you will. So OpenCV, I will mention one last thing about it. It's divided into two parts we call core and contrib, like contributions. Contrib is kind of a little bit more of a Wild West around the core of the library. So if you want to have a pull request accepted into core, the standards are extremely high. Contrib allows for a little bit more sort of laissez-faire attitude and things to enter the library a little earlier before they're really bulletproof. Very few things are actually added to core other than maybe bug fixes that aren't done by the OpenCV core team, whereas Contrib is mostly from outside. In many cases, things from Contrib will be re-implemented by the core development team before they end up in core, just to absolutely guarantee the quality. So some resources here, which I'll skip by real quick, but when you watch the video, for our viewers at home, you can pause. OpenCV main site is opencv.org. The developer site is on GitHub. You can download the package from opencv.org. It downloads .html. There's documentation on the web. There's quite a bit of it. Since the original book, the internet itself has gotten a lot bigger. There's a lot of really nice documentation out there, fantastic tutorials, and also other people have written some pretty good books. Our book was originally using the C library, which was all there was back in those days. When we wrote OpenCV3, or Learning OpenCV3, we modernized it all to C++, but of course there are very fully featured Python and other language bindings for OpenCV now, and there are some fantastic books that have been written by people on OpenCV that sort of natively talk in terms of those languages. So basics of key points. What are key points? What are we all here to talk about? So here's my intuition for key points. This is what I tell everybody to think about. This is how I'd explain key points to like my mom, right? Or just anybody who cares. So if you're doing a jigsaw puzzle, you all done jigsaw puzzle? Raise your hand if you have not done a jigsaw puzzle. Okay, everybody's done a jigsaw puzzle. You know what I'm talking about. So you dump out the pieces, and what's the first thing you do? Well, you assemble the edges, and that has nothing to do with what we're talking about now. So what's the next thing you do? The next thing you do is you kind of rummage through the pieces, looking for ones that are like really identifiable, right? If you pull a piece out that looks like, does the pointer work, like that, or a piece that looks like that, you can look at that piece, and by looking at the box that the puzzle came in, you know right where to put that piece without any other pieces, right? And in fact, if I showed you just those two pieces, I said, what do you guys think this is a picture of? This building? Anybody?
Cathedral.
Getting closer? Yeah. So you already sense that it's some sort of massive edifice made of stone. Anybody want to? Closer? Nobody can quite guess. So maybe these 2 key points weren't enough. But if I give you 10, I bet you could guess what this is. I'll show you. What? So if you had a few pieces of this puzzle, of course you could have guessed they're puzzle pieces, so it has to be that castle in Germany, right? Like all puzzles are that castle in Germany. But in fact, those are drawn from this picture here, right? And there's that little a little cupola, and there's the top of that spire. And you could just look at this box, and you'd know exactly where to put those pieces. Now, that's because those pieces have most of the information content is there, right? The pieces that are up here in the sky, these are really hard to, and they don't have a lot of information in them, right? So what you do when you assemble the puzzle is you first work at the parts that have all the information, and then you suffer through the rest. Now, in computer vision, often algorithmically, you can just solve the part that has all the information and just ignore the rest, right? And that's what you will often do. When you're confronted with multiple, you can solve a lot of problems with these kind of pieces. So for example, you can ask, are these 2 pictures of the same thing? Well, you as a human being, you do this so powerfully and magically that you don't even know how it works, okay? But if you were a computer, you'd have to be a lot more specific. And these are the same castle, right? This is the Swan Song Castle in Germany. But this little cupola, you see, it looks almost identical to there. It's rotated, of course, but it's very, very similar, right? And similarly, this spire here, which is, of course, rotated a bit, but looks very, very similar to that spire there. So you might imagine that if we had 2 puzzles, right? Each of us had a box with a puzzle in it, and say, are these the same puzzle? Like, let's say we'd long since lost the boxes. Like my grandma used to have them in like white and brown paper bags, right? So what is this a puzzle of? We could just pick out a couple of really good pieces and compare those. And if we decided they basically matched, we'd be pretty sure it was the same puzzle, right? So that's the basis of object recognition, right? In the case of key points. Also, you know, if I think a little more abstractly about the relative location of these things relative to each other, well, just 2 isn't going to tell me much. But let's say I had this tower top here, right? Well, those 3 things, if I start getting more and more of these things, I can tell by their relationship to each other what angle I'm viewing the castle from, right? Now, of course, I can't do that just with the pieces in my palm. I have to figure out where they go relative to the puzzle. But if I've done that, then I can just compare them and I can figure out the angle I'm viewing from. We'll return to that stuff later, but that's just kind of whet your appetite for like, this is actually a pretty cool set of techniques. These key point techniques, before deep learning came along, had become one of the major tools in computer vision for solving just about any problem, right? So you'd take just about anything, you'd extract a bunch of key points, you'd throw those key points into some learning thing like a support vector machine, and you'd basically be done. So let me talk about some specific features and kind of the history of key points and how they came about. So I'm going to talk a little bit about what are called Harris corners. There's sometimes called Shai-Tomasi features. It's probably Shi-Tomasi, but everybody says Shai. So I'll say Shai-Tomasi features. The Shai-Tomasi feature is just basically a slight improvement on the Harris corner. The Harris corner really launched this whole industry. So these are just some pictures that show some of these Harris corners to give you some kind of intuition for what turns into a Harris corner. I'll talk in a minute about, we'll look at the mechanics of it, but the white dots are Harris corners. And I'll show these for some of the other key point types, so it'll give you a little intuition for how they differ from one another or how they're similar. So the earliest kind of key point, the Harris corner, what's the intuition on this? Well, they were the problem that people were interested in at that time was tracking. So let's say you have 2 frames in a video and you want to know, where something has gone in the video, something like that. And the idea was if you look at just a small patch in the image, then like here's some zoom in. I don't know if you can see there's some red crosses here. There's 3 red crosses in the image. So each of these 3 red crosses, this is from Selinsky's book, which is a fantastic computer vision book, much higher level than this talk, but I stole his image anyway. If you look at this is just some greedy stuff turns into that, right? Or actually probably this one turns into that. And then this edge here, this is coming from the roof edge here. So when I look at these things, let's say I looked at this image and then I had another frame in video, it had changed a little bit, right? Like the video had moved or the house had walked along or whatever. I mean, could happen. So I want to know, where did those things go? Well, if the thing looks like this, if it's a very sharp peak, then if it's moved a little, it's going to be very easy to find that peak, right? But if it looks like this and it's just a mess, then if it's moved a little, it's just going to be more mess. The 2 things, I'm not going to be able to find that particular mess. It doesn't look any different when I slide it around, right? Now this is kind of an interesting special case. If I move perpendicular to the line, it's very easy to like realign it to figure out what I have to do to, how much transformation has happened. But if I move along the line, then it's anybody's guess, right? So this is the basic problem that people were looking at, and the intuition was, if I have a feature like this, which is strongly differentiated in every direction, then if it moves a little, I'll be able to find it again, okay? So there's going to be some slides like this. Okay, this isn't to intimidate anybody, but if you're the kind of person who likes slides like this, I wouldn't want to leave you out, okay? So this is the sort of mathier kind of slide. I don't think it gets much mathier than this, though. So this is the whole, like, Harris corner, Shai-Tomasi thing in a nutshell on basically one slide. But the idea is, do you want to find these places where changes in the intensity that result from shifting the window in any direction will be very large? That's kind of the way to turn it into a math problem. To say that if I compare this image to what I get if I slide it a little bit, right? That's called autocorrelation. And that tells me something about how unique it is, right? If it's just a flat white and I slide it a little, it's going to look exactly the same, right? So that energy cost is 0. This value E gets very large if the image is like the one on the left from the previous slide where it's got that sharp peak, okay? Because then everything is different, right? So there's a little bit of math here, but basically the idea is I take a little window around that point and I compare the difference between the intensity at all the points in the window and like sliding over the window, right? The effect of having transposed it a little bit for this window W, and I look at the square difference of the intensities if I displace it a little bit. And in that thing, if I want, I can express it sort of in this form. I'm not going to dig into this math too much, but what it really boils down to is I can express this in a convenient way in terms of derivatives if I have some belief that this image can be treated as a kind of continuum object, right? And your intuition should back you up on this, right? If there's a strong derivative and you move the thing, then it will change a lot, right? That's not rocket science. What is a little more subtle that you just have to kind of do the math is you recast this into this form, you end up with these two derivatives. The second derivative is basically showing you the curvature, and this is basically curvature in another direction. I can recast that into this form, I get this matrix. This is the interesting part. This is the matrix of what are essentially second derivatives, and it's basically telling me that where there's a sharp curvature, then there's going to be a lot of energy for moving it, right? And the energy is really just the sum over the window for that function, for that matrix, or compacted over that matrix. So when I do this, the interesting thing here is my intuition says if it's like strongly curved in both directions, but then which directions? X, Y, of course now it's a linear algebra problem, and I want to think in terms of the eigenvalues of this matrix, right? Because it's not obviously aligned with any particular axis. Now, when Harris came along, he came up with this kind of funky formula that said, well, if the determinant of the matrix is much bigger than the trace of the matrix times some magic number, which he published, then it's good. And it was very not so intuitive. Shea and Tomasi came along later and said, that's a lot of work. Why don't we just set a threshold on the minimum of the two eigenvalues? As long as they're both kind of big enough, then we'll say that's a point worth tracking. Okay? And indeed, Shea and Tomasi's paper was called Good Features to Track. And that's sort of the key point mentality is sort of sneaking in there for the first time. So what's important to take away here is this function is going to be evaluated for every point on the image, okay? And at some points, this criteria will be met that says there's kind of these strong local curvatures, and those points you're going to kind of keep in mind because they're interesting. Those are the good puzzle pieces, okay? And that's important because an image of potentially very large size can be reduced to a much smaller number of key points. It might be 1,000 by 1,000 image, and it turns into 400 key points. The other thing that's interesting and maybe a little less obvious is that implicit in this is this window, which is of some size. The size of this window makes sense relative to the size of the image. So if I double the resolution of the image, I'm probably going to make a bigger window. And one of the neat things about that is the key points don't necessarily grow in the area of the image in terms of pixels, which is very useful, right? As we go to higher and higher resolution image, what we'd want to find is sort of the same number of important things, but we'd want to know more about each of those important things rather than have an exploding number of important things. In some sense, 10x the resolution is not really adding information, probably according to your intuition or mine, so you would like your algorithm to kind of respect that. So here's Shea Tomasi Operation OpenCV. This is an old interface. I'll talk a little bit about how it's done today in a little bit, but I'm just going to sort of show you this is what happens when you actually go call this function. I give it some image. I give it an output array where it's going to stuff all the corners. The corners just have XY coordinates. I tell it the maximum number of corners, how many I'm willing to tolerate. I can set that very high. It may not produce that number, but at least it sets an upper limit, which is obviously useful in the computer environment. The quality level, I'm going to talk about that. Let me come back to that in a moment. The minimum distance, what this does, it says, sometimes there'll be corners that are basically right on top of each other because it's a strong local structure. And this basically says, just keep the best one within that range. Don't give me like 20 corners that are basically on top of each other. The mask is useful if I just want to not know about certain corners, like I'm tracking an object and I already kind of know where it is. So like don't bother searching for corners far away from the object I'm tracking. The block size, this is saying this neighborhood in which the corners are going to be computed. This use Harris detector, basically this says, if I don't say use the Harris detector, it'll use the Shea Tomasi metric. If I tell it true here, then it will use the old style one that nobody uses. So nobody sets that to true. Now, and then if you're actually using the Harris metric, then you have to give it that magic K parameter, which is typically 4/100ths for no apparent reason. Now, the quality level, I told you I'd return to that. What that basically says is, remember that, let's say we're using the Shea Tomasi metric, then the quality of a key point is the minimum eigenvalue. That's the thing that had to be thresholded, right? In the Harris case, it's the output of that complicated function. So, of course, some of the things are going to be way better than that, and some of them are going to be kind of marginal. If I set this quality level, let's say I set it to 0.5, it's going to throw away anything that's less than half as good as the very best one. Okay, and that turns out to be an extremely useful tool. Here's just a little example. So, good features to track, pick out the 25 best corners here. The quality threshold is set very low, so basically as long as they're good, but it's going to keep the 25 best. Throw away any overlaps that are within 10 pixels of each other, this simple test image, and the corners come out basically, you sort of figure out that's why they're called Harris corners, right? They kind of come out where you think they would, right? At these three-way junctions of things where any displacement would cause a big change. So now I'm talking a little bit about optical flow. Not too deeply, this is not really the subject of this talk, but it relates to Harris corners and it's a useful thing to understand. So these guys, Lucas and Canati, this is a very famous paper, they were interested in how to track motion in an image, and originally they were thinking in terms of tracking motion in a continuum way. So they wanted a kind of vector field where every pixel was assigned a velocity relative to some new frame in a video or something like that. But it was quickly realized that that's actually not going to work, because obviously if you have like a giant patch of uniform color like the surface of whatever, one of these desks, then obviously you're not going to get any optical flow information across that. So what people quickly learned to do is apply Lucas and Canati's technique, but only apply it to the points that were already identified as good points to track, right? Hence the name. So instead of trying to do it with the whole image, it might be 1,000 by 1,000 image, though in those guys' day it was probably 200 by 200. But they just apply it to those individual points. So for the points you knew you'd get a good answer for, then you go apply their technique. And what was their technique? Their technique was, well, we make some basic assumptions. This brightness consistency that says as a point moves from frame to frame, it's not changing brightness radically. Temporal persistence that says that the thing doesn't just disappear or reappear, right? These things all get violated. This specular reflections, occlusion would violate this, but in general, they're reasonable assumptions. And then this spatial coherence is basically saying that whatever it is that's moving, the whole thing moves. The things near it move close. And again, right near an edge, that may not be true. But it turns out that if you make those three relatively reasonable assumptions, you can create this optical flow algorithm that will, basically, if you sort of think about how this is going to work, I build a sort of a continuum function in the proximity of whatever I'm trying to track. Like it looks like a bump, and then I'm going to look for that bump a little ways away, right? And then I'm going to compute how far it's moved. So the optical flow algorithm is relatively straightforward. Again, a little beyond the scope of this to give you another one of those big mathy slides, but it's a very simple idea. But the key takeaway is when you want to try to look at the structure moving from one little area of the image to another, there had to be some structure in the first place. So you use these good features to track, and then you feed those to Lucas and Canati's algorithm. This is how optical flow works in OpenCV. I'm not going to go through it in great detail, but you give it the previous and next images, in your video sequence or whatever. You give an output for the points, and you you give it a list of points. This is the output for the prev points, is the output from some kind of good features to track sort of analysis. And then it will try to compute the next points, figure out where those go, and it will tell you if it was able to actually find that particular point or not. Again, that's probably the most important thing. I won't get into the other details so much. Most of them you can leave at their default values and things will work out fine. So I want to introduce this idea of a key point descriptor, because when you're doing this optical flow algorithm, you have to find the thing, right? And so how do you find the thing that moved? You have to have some sense of what it kind of looked like in some way so that you can recognize it, right? And Harris corners aren't normally thought of that way, but just to build a little intuition, I'm just going to kind of draw you back to what we talked about the Harris corner. The eigenvalue matrix, I called it eigenvalue matrix M, but that's a little weird to say. The matrix M and its eigenvalues, that matrix M has basically three free parameters in it, right? Because remember, it's symmetric. So those three parameters, basically, they kind of identify that corner in a way, right? There's some other thing that's very smooth or very sharp in one dimension and not in the other or whatever. And then there's some intuition that I could sort of use that to describe a particular corner. The problem with that in practice is that's not a lot of parameters to describe. You're not going to be able to tell the difference between some of those different parts of the castle I showed you with that simplistic representation. But have that in your mind as kind of an intuition that I had some notion of how the key points were going to work, and then based on how they worked, there are some kind of parameters that parameterize them that I could extract. This is simple, there's 3 parameters. That's not what you need. You need a lot more than that. You'll see later on that there'll be 100 parameters or something that'll be a lot more typical for the key points you use in practice. But this is just for intuition building. And so let me talk a little bit about how key points live in OpenCV. They're sort of generalized. And there's a key point object, CV key point, no surprise there. And the key takeaway from this is all the key points we're going to talk about can be talked about using this one kind of object. So whether it came from this or that or another key point algorithm, pretty much all key points have the same set of basic dimensions. They live at a particular place in the image. They may have a size. Not all key points have a size, but most have a size. They may have an angle, meaning that key point may have some kind of sense of orientation. Okay, may not, but it may. This response, this is kind of like, remember we talked about the quality with the Harris corners, right? There's some kind of quality metric that's telling you like how key pointy that particular key point is. Now, it's not always going to be the same in the sense that this response might be 0 to 1 for one kind of key point and 0 to 256 for another kind, but they all basically have some response quality metric. This octave, this will come up in a little bit, but what this is that when you...
Could you elaborate, give us an example of response?
Well, in the case of the eigenvalues, the minimum eigenvalue of a Shai-Tomasi point is the response. It's sort of the thing that gauged its quality, right? The things that have a very high minimum eigenvalue are things that have a very sharp curvature in both directions, and as a result, they... I'm going to change this. I somehow changed this thing. What happened there? So they have a very high response, and so that's the sense of their quality. For different key points, it may be slightly different, but in general, it's something of that kind. Whatever it was that got threshold to tell you that thing was a key point in the first place, it's probably going to be that thing that's the quality of the key point. With regard to the octave, when you have a system, like in the Harris corners, the key points are kind of point-like, right? But in many cases, there's a sense of how much area contributed to their existence. And so, and we'll see that in more detail in a moment, but whenever you're looking for something that's a variable size in computer vision, the way you almost always do that is instead of like convolving an image with things of different sizes, what you do is you create a pyramid of those images of different you scale down the image in steps, and then you run your convolution over all the scaled images. If you just think it through, that's much more efficient computation, right? So if I have an image that's 1 megapixel, and I could have a scaled pyramid of images, the next one's half a megapixel, the next one's a quarter megapixel, they're going down, down, down in resolution, then in effect I've only doubled the total compute cost from the original image to create a pyramid that goes all the way to 1 pixel, right? So that's a common trick in computer vision. This octave is saying where was this particular key point found in such a hierarchy, if such a hierarchy was relevant to the key point type at hand. And then the class ID, this is a general integer that will sometimes be used when you're using key points, either cluster or identify things. If the key points are associated with a particular, like those key points are all part of that particular book cover, then those might be given the same ID. In general, this is used by other algorithms that process key points as an output, right? So some of these slides get a little dense, but it's because I wanted to put some chunks of code in here. You don't have to memorize all this. It won't be on the test. But when you search for key points, the key points themselves are absolutely generic. The algorithms that find key points, obviously those algorithms are different in implementation, clearly. And the way that that's handled in OpenCV is there's this functor class called feature2D. So, well, not technically a functor because it doesn't have an overloaded function operator, but it's sort of a function object called feature2D, and there's going to be one of those for every kind of key point detector. The intuition being that all key point detectors do the same thing, they detect key points, and they output those key point objects, which we already decided were going to be kind of generic, but the algorithm itself is going to be different. So every one of these feature2D derived things will have to have a detect algorithm that you can take an image and it will spit back a bunch of key points. It will have to have a compute algorithm where you can give it an image and key points and it will spit out the descriptors for those key points. And then commonly you do those things together, so there's some economy in just calling a single combined function that will do those things. And then you often want to query them, so you want to just ask this, you happen to have such a feature detector object lying around, you want to ask, how big are the descriptors that come out of this object, for example? Are they 100 numbers? Are they 500 numbers? You use those things for memory allocation and so on. Read and write. These file storage and file node structures are used in OpenCV as a convenient way to store stuff to disk. So that's just a useful convenience function. So I'm cruising through kind of the generic part, and then I'll dig in on some specific key point types, and then it'll get a lot more clear. But the key takeaway here is CV feature 2D is an algorithm class object that is kind of the way in which all these things are done, and every kind of key point descriptor you might want to compute is computed by something derived from this. This is extremely useful in practice because it's very easy to say, create a pointer of type CV feature 2D that points to a particular feature detector, and then you pass it stuff, it gives you answers, you do computation, and then you wake up one day and you think, maybe I should have done this with this other feature. And in like one line of code, you change that, you create one of the other feature type things, point that pointer to it, and the rest of your code doesn't change, right? So it's extremely useful in practice. It is very, very, very common that when you're writing code that uses key points, that you will experiment rather voodoo-like method of experimentation, trying various kinds of key points, even ones that you don't think will work, just in case you get some insight from them. So the last thing is the key point features, or the descriptors. So every kind of feature ultimately can produce a descriptor for its associated key point type. There isn't a specific class to handle these descriptors because descriptors by their nature are just vectors of numbers. Okay, so they're just handled using the native OpenCV array type. Often you have a big pile of them. Most of the time they move around in piles, so it's quite common to have a two-dimensional array in which every row is one of the key points, and there are just many, many rows, right, for all the different key points in that particular output. So that's the return type, for example. If we go back and look at, if we look here where it says detect, and then we compute, we get the descriptors out just as output array, right? This is an m by n matrix where m is the number of key points and n is the descriptor size. So the big, just this is the key point, okay? Well, here we're there. Okay, so the descriptors in OpenCV just vectors and numbers, okay? And we usually just pass them around. They're just stacked up in what will look kind of like an image, I guess, but in a 2D array. So let's return to the Harris corners for a moment and just see how they look in kind of new OpenCV. Because good features to track was in OpenCV way back in like 2008. It's ancient. I think Harris wrote the original Harris corner paper in like 88, and I think that the Shitamazi variant of that was published in like 94. This stuff is old, okay? So it was in the old versions of the library. But now, later, key points have become a really central part of the way computer vision is done, and so there are lots and lots of key points, and so OpenCV has this nice, object-oriented, class-friendly, C++ sort of became a thing in the meantime. So, that's all implemented now. So even for convenience and compatibility, even the good features to track, the Shitamazi features are implemented on top of this feature 2D interface. And that's a nice sort of branching point for us because it will show us how the new interface works. But basically, it's very simple. There'll be some class, GFTT detector, that's good features to track. And it's derived from feature 2D. It has all the normal junk. It also has this static create member. And so this is a very common trick in the OpenCV library. You'll see it all over the place. You'll see some kind of base class thing, and then there's sort of a derived class off that derived class. And then when you want that derived class object, you use this static create member. That's just like, you'll see it all over the place. The developers in Russia love this construction. So the way that works in practice, I say CV pointer, a CV pointer is like OpenCV's version of a garbage collecting smart pointer, right? CV GFTT detector, my detector, and then I just call this create member. Of course, since it's static, I can call it from outside. And then when I want to do something, I just say my detector, detect and compute, blah, blah, blah. Again, the key takeaway here is that my detector happens to be of this type. Actually, I could have declared this as CV pointer of CV feature 2D, which would have actually been a little bit cleaner thing to do, right? Because then I can call anybody's create method, and the rest of the code would just sort of do the right thing, hopefully. Okay, so that's it for the little blast from the past. We'll talk about modern key points. So This might be a time for anybody, you have any questions on stuff that's going by? I know I've been a little bit cruising along, but this is a good time to like. So far, so good. Okay.
Cryptography can be defined precisely as destroying all visible key points.
Huh?
Cryptography is an algorithm that successfully destroys all key points.
That would be true, or at least all key point descriptors. So let's talk about a particular feature type that's very popular. So there's a giant zoo of these features. And when I originally planned this talk, I thought, yeah, I'll go through a couple of them. I'll go through 10 of them. And then I thought, maybe 5, maybe 4. I think I got down to 2. But it's not really crucial to go through every last one of these. Little book plug, they all in the book, other than ones that have been invented since then. But deep learning kind of put an end to people creating new features, so that's good. So what the SIFT feature was one of the first really important features in the modern era. Okay, so this guy, David Lowe, created a kind of feature which was very powerful. It has a lot of nice characteristics that the Shai-Tamasi features don't have, and became kind of the foundation for how people looked at the key point, what later became sort of the key point industry after that. For a decade, people sat around thinking of new key points. If you look at this image here, here's 2 cars, or the same car from a slightly different viewpoint. And some of the things you'll notice is, first of all, you'll notice these key points have a size, right? So I mentioned that at least a little bit, foreshadowed it. You'll notice this arrow here, this line, which is suggesting something about the orientation of that key point. And then if you're really paying attention, you'll notice that the number of these key points, which show up over here, is actually a lot bigger than it was in the Harris Corner case. These key points are a lot more stable. So this thing is huge, right? And it somehow captures some characteristic of this entire corner, this line, the hood, the light, and you see it over here, right? And there it is. And same with this one. This one somehow captures something about that part of the fender. And you see over and over again, this even here where to your eyes, this looks a little dark, of course, because it's a black area and this is a projector, but there's definitely data there. And you can see sort of the top of the wheel is again captured. And there are things that aren't, whatever this big thing is, isn't over here. Key point techniques are not 100% reliable in that way, but often there are many features that you do find, this feature, they both reappear. And that allows you to make very good associations. Sort of the hypothetical or theoretical promise of key points that I kind of alluded to in the last 10 slides starts to really happen with the SIFT key points. So let's dig into them a little bit. So how are SIFT features created? So SIFT features, they have, I'll talk about sort of how each of those elements of the feature come about, the scale and orientation and so on. So one of the interesting innovations is they're based on what David Lowe called scale space extrema. So the idea is you start with the image, you make a pyramid of those images. So you have slightly different scales, okay? And then you convolve them with Gaussians. Now that's equivalent to taking one image and convolving it with Gaussians of different sizes, right? Depending on how you want to think about it. It's intuitively a lot easier to think about it the latter way, but you're kind of a silly person if you don't implement it the former way, right? So let's think about it in terms of a bunch of Gaussians of different sizes being applied to images of the same size, just because it's intuitively a little easier. So what's going to happen? What happens when you convolve something with a Gaussian? Well, you get kind of a peak if there's a blob of that size there, right? And then what he does is he's sort of, in some sense, he's looking for a response for blobs of different sizes, but he then differences every sequential one. Okay, so what that's telling me is that there's kind of I'm at the edge of that blob, right? If you sort of imagine a dinner plate, and I convolve with Gaussian, I go bigger, 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 bigger. At a certain point, then the Gaussians that I'm convolving are going to start to just smear it away, right? So I don't see anything there. So what this difference does is it helps me find sort of extrema in this different space. And if I look for individual points in what is now kind of a three-dimensional structure, right? This is the image xy, and then this is the different scales. Then if I don't know, you can't see this super well, but if you look at this point here, it's surrounded by little x's. If there's one point where that difference is higher than all of its neighbors in both xy and in scale, then that's what Lowe calls a scale space extrema. That's sort of telling me there's a thing there that is about that size at that place, right? So that's a very useful construction, okay? Now, this is a very useful aspect of these SIFT features, but as they say on late night television, there's more. So another thing that these features have is orientability. And the orientability is an extremely powerful element of it because it means that you can recognize it when it's been rotated, right? Whereas if you think about, for example, in the case of the Harris corner, if you rotate it, those 3 parameters in that matrix get all mixed up, right? So here, what happens is you take the region around the point that you found, okay, and you divide it up into some number of small cells. These could be individual pixel level, or they could be blocks of pixels, doesn't really matter. And what you do is you calculate essentially the directional derivative in that little area, okay? So that it's easy enough, you have a x and a y sort of gradient-like operator that's defined, obviously not continuum gradient, but it's, some passable lattice analog of a gradient, and you have an x and a y part, and you combine them to get a directional derivative that has a magnitude and an orientation. And then the idea is you grab up all those directional derivatives, you weight them with a Gaussian so the ones in the middle have a little more meaning, and then you build a histogram out of them and say, okay, how much derivative do we have going left, how much going up, how much going to the right, and so on, okay? And then by doing that, you can say, there's a peak, there's this one here that's like really the direction everything points. And then it turns out in practice, I don't put it on the slide, but you actually fit a little thing here and you do a little interpolation and you get something that's not so discretized as the histogram. But the key idea is this thing that's sticking up in the middle, right? If you were to rotate this object, right? If you took that car and you flipped it over, what you'd find is that this thing that pointed to the left would, that peak would move over here and point to the right if you flip the car over. So that's a really nice feature, right? Because it means or feature is a little overused here, but if you're using this particular kind of feature, anything with this sort of construction built into it, it means that you can recognize its orientation. It means you can find it when it's been twisted or flipped or whatever, right? And now for some things, like if you're looking for people or cars, they have a certain intrinsic orientation most of the time. But if you're looking for something like a book, right, then if it's sitting on the desk, you see the cover of the book, it's very likely to be at a random orientation relative to the camera, right? So let me talk a little bit about finally what the SIF feature actually is. So the first thing, it's got a size, then it's got an orientation. So once you've computed that orientation, I got this from somebody on the web who obviously put a lot of time into this really beautiful image. I don't know who they are. Google found them, but my gratitude to them for this really beautiful image. They took a lot of time to do this. So what the first thing you do is you compute the scale, and then you kind of normalize it. Then you compute the orientation, and then you twist it so that in some sense that orientation vector is always, let's say, up or something like that. Now you can compute the descriptor in a way that's essentially orientation invariant, right? Meaning because I corrected it, next time I find it, I'll twist it to 12 o'clock before I compute the descriptor to do any matching. So how does this work? This is a rather tricky construction. This is the kind of thing you look at and you think, how did anybody think of this? But it's a long evolution of smart people, and it sort of ended here. So what is happening, this is typical numbers for an actual SIF descriptor as published in Lowe's paper and done to this day. The space around the SIF point after rescaling and orientation correction is then divided into first a 4x4 array of cells, that's the heavy lines, and then every cell a 4x4 array of subcells, okay? And these subcells are basically pixels, but remember we've already scale corrected, so the term pixel is a little awkward here. But each of these subcells, I then compute the directional derivative in the subcell, and then across the entire cell, I compute a histogram very similar to the one that I use to give an orientation to the overall device, okay? And there's a weighting factor, Gaussian weighting factor. So when I add up the contributions to all of those histograms for each cell, what I get is I get a histogram for that cell. So in this case, there's 8 orientations. It's actually more common to use 16, but whatever. So there's this number of orientations inside of that cell. So now what I have is a 4x4 array of cells, and in this case, 8 orientations per cell. Okay? So 6 cells, 8 orientations. Oh, actually, I take back what I said earlier. 8 orientations is the normal number. 128 different numbers that are being derived from this picture, and that's actually the descriptor. Sometimes people use 256, so they double the number of orientation bins. But this descriptor actually really captures a lot of information about that thing, and it does it in a scale invariant way. So this one that's really guards that window that's a certain size, there's a different one that's quite small, and it's got some very detailed stuff inside, and this always kind of normalizes all of that out. Yeah?
So when it comes to the Gaussian weighing part, is that per cell or is that with respect to the center of your entire?
In the case of computing this descriptor, I believe it's centered on the overall structure and decays out. Then I believe it's 1.5x the size, the half length of this or something like that. I've forgotten. But there's a pretty standard prescription for how to do this. But in any case, you will not do this, right? Because smart people worked really hard to do this in the OpenCV library in a very high performance way. And you have very low probability of beating them, right? Because those people had been charged with the rather holy task of doing this once for the benefit of all of humanity, right? Because that's what OpenCV is for, right? OpenCV is not there to itself push computer vision forward. People don't put new algorithms in OpenCV, right? People put algorithms in OpenCV that everyone has agreed are really important. It's kind of a ratcheting effect, right? Once something is, everybody says, that's really important, we're gonna use that a lot, the whole community is excited about it, then it goes into OpenCV, and some people work really hard to make it a really high quality building block from which people can then move forward without having to constantly reinvent the wheel, right? So OpenCV's whole concept is to take good ideas that the community has accepted and turn them into highly reliable, high performance building blocks on which people can then build the next generation of new algorithms. So this is how SIFT works in OpenCV. You'll notice that there's this class called SIFT, which is derived from feature2d, which is exactly what you would have expected given what we saw in the good features to track. And what are the parameters? It's the same sort of concept of this static create method. And we pass it a couple of things. The number of features to use. We tell it the number of octave layers. This is saying, it's the number of layers in an octave, but this is telling you basically how finely to grade the scale space search, right? So yeah.
So do you get a 128 dimensional feature vector per key point, or is
That's
it
correct.
the entire image?
No, that's correct. Every key point has a 128 dimensional descriptor.
How do you, let's say if you have another image and it has fewer key points, and how do you match them across different images?
Hold that question because we have some slides for that, but that's the kind of question that people went off and thought hard about, and eventually the community came to some relative consensus, and then the OpenCV guys went and implemented what everybody seemed to think was the best way to go, and then I'll show you how that works. So we'll get to that. This contrast threshold is just there to throw out weak features. These things, if you take a look at the book, for example, there's some description of how these things all work. But the basic truth is you don't need to change these very much at all. You can just, use the default values. Now, one thing, a warning here, I put down here, SIFT is not available under the usual MIT license. So there's a patent on it, and University of British Columbia, I think, where David Lowe was a professor, and there's some rules for licensing it if you want to use it in a commercial product. And unfortunately, those rules are rather incompatible with with the MIT license, which is the bulk of the library. So this particular feature is, though it's of class feature2d, the library it's in is called xfeatures2d as opposed to features2d, which is the open source one. This is in contrib, not in the main build. So no big deal if you want to use it, you'll barely notice, but it's something to notice if you want to use it in a product. You need to be aware of that. And that's why it's separated into this subcomponent, which can have different licensing rules. So I'm going to talk about a different feature now. So Orb is one of the latest features. So tons of features happen in between, and I'll reference a few of them because Orb is based on them. But Orb feature is a very different approach. Their Orb features are designed to be extremely, extremely fast. And over the almost 10 years between SIFT and Orb, people learned a lot of things about what you do and what you don't need to represent, what you can sort of get away with throwing out, what you absolutely have to keep, and so on. And the Orb features are one of the preferred features in the modern era for any kind of high-performance environment. SIFT features are still more expressive, and they're still quite heavily used, but Orb is what is used on almost any mobile applications and any kind of performance critical applications, Orb is probably the standard. There's a few features that kind of derive from Orb that are coming now, which people may be using, but Orb is a good choice. Just something to stick in your head. If you think you want the highest performance feature in terms of quality and recognition, and you don't really care about speed or money, then SIFT is probably still the best bet, or at least a very strong contender. And if you want the highest performance in terms of compute, and you don't want to spend any money, and you're willing to have a little bit less expressivity or reliability in the feature, then Orb is the way to go.
What do you think of Surf?
Surf is sort of derived from SIF. It's also a very powerful feature. Surf is usually oriented, and so often Surf will perform better when you're in an environment where you have some intrinsic orientation, like pedestrian detection and things like that. But yeah, there's a huge zoo of these things, and in the book there's quite a menagerie that you can study. So let's look at these Orb features and see how they work. So the theory behind the Orb feature is to capture some of the goodness of both SIFT and even the Harris Corner, but in the most economical possible way. And so what an Orb feature does is it considers just a ring of points, typically 16 points, in a circle around the one point that you're currently considering. And then it just divides those points into two kinds, the ones that are brighter than the middle and the ones that are less bright than the middle. I guess if it was equal, then maybe it throws it into one or the other bin. But what it then does is it just looks, so these things gets converted to basically a binary string, and then as you move from one to the next, there's a requirement that for something to be a valid Orb feature, for a particular pixel to be considered an Orb feature, there have to be more than a certain number in sequence that have the same value, meaning 1 or 0. These are very fast operations to apply, right? And so if you think about, like, look at this feature here, you see how there's kind of a bunch of black ones here, and then they kind of get light going around? Like, this is, you think about the intuition from the Harris Corner, this is a good sort of Harris Corner as well. But this is a very fast thing to compute compared to a Harris Corner, okay? And so this feature here was actually originally, this feature type was called fast before it got absorbed into Orb. But the feature called fast is a very, very efficient way, very compute-friendly way, binary operations, very simple counting operations, to tell you whether or not a particular point is sort of a good feature, okay? Now the descriptor, later on people got into this kind of like, my chocolate and your peanut butter, put the monkey head on the elephant, sort of like, because the descriptor is not fundamentally tied to the feature, right? I mean, in some sense it seems like it is, but I could always apply any descriptor algorithm. I could choose to apply a descriptor to any point in the image, right? And I could choose based on the feature that came packaged with it, or not. I could use the SIFT algorithm to find the feature, and then just throw away the SIFT descriptor and evaluate some other descriptor at that point. And in fact, in practice, real professionals find that they actually do that with some productivity. But, and then often you get these things that are like stable hybrids, like Orb, which took its feature, like Boolean, the decision as to whether or not a pixel was a feature, kind of took that from this prior entity called fast, and then its descriptor really was taken from something called brief, which was a different descriptor, but they added some extra machinery, so this would be orientable. And it was quickly found that people really knew from SIFT and other things that orientable feature is extremely powerful. And so there was a lot of desire to use those, and that's Orb actually stands for orientable brief. Now, there's another thing that I don't really have on the slide, but I'll draw your attention to it, which is people are very interested in features being robust to affine, small affine transformations, right? Because if I'm looking at a car or a building and it's moved a little bit, like I'd like the location of the features to move in the way that sort of projective geometries would suggest, but I'd like the features themselves to still be matchable and findable, right? So if the feature is really big and the thing moves in such a way that, a planar, let's say it's, text on a planar surface and it moves, then it's going to get squashed or stretched or whatever, and we'd like the feature to be kind of robust to that. That turns out to not be such a strong characteristic of SIFT, but it's a very nice characteristic of fast, okay? Because fast just uses this ring, and so you can imagine that if you kind of displace this thing a little bit underneath that ring, it wouldn't really change the result that thing was a key point. Now it might change the descriptor, and we'll talk about that in a second. So So orb is fast, which we didn't talk about, plus brief, which we didn't talk about, plus some extra secret sauce. But I basically told you everything you needed to know about fast, and now I'm going to tell you everything you need to know about brief. I'll tell you briefly. So when you compute a brief feature, well, hang on. Before I get to how brief works, let me just talk about the orientable part. So the way that these things are oriented is very simple. Again, the idea when orb was created is to make it fast, as fast as possible. So really tried to solve problems in ways that were very friendly to the computer, right? SIFT is kind of friendly to the goals, if you like, but not really amenable to the way computers work, right? A lot of cosines and sines and directional derivatives getting calculated, stuff that's like not very friendly to your compute budget. So with orb, to create this rotational invariance, a very simple idea. They just take the region that the feature applies to, okay? And then they calculate the centroid, the first moment, basically the average in x and y, okay? And that gives this centroid. And then whatever direction it is to the centroid from the center, that's the orientation. And it turns out this works really well, okay? This works just about as well as SIFT's orientation, even though it's incredibly simple to compute, right? Because this is just a running average over these two dimensions, right? You don't even have to divide, really, right? So that's how you get the orientation. So once you compute the feature, then you can compute this orientation vector, and as with SIFT, you kind of rotate it back to 12 o'clock before you calculate the rest of the descriptor. So let me show you how the descriptor works. The descriptor is computed according to this brief algorithm. And here's how it works. It's a little bit strange, but again, it's very, very fast. So imagine that you have a bunch of random pairs of points that are within the region of the feature. They're just random pairs. It could be anything, okay? But it's always the same, right? You don't change it on a per feature basis. Just once you decide, okay, this is what it is. And by the way, in OpenCV, it's just coded into OpenCV, like some particular reasonably effective random string of these things. It's kind of like if you took a box of toothpicks and poured them out on the table, right? You'd get like a bunch of little lines. And what's going to happen is every one of these things, there's the first one, the second one, third one, fourth one, whatever. Unlike toothpicks, they're sort of random lengths. And what the descriptor does, it simply takes the first one and it compares the beginning to the end. And if the beginning is brighter than the end, it assigns it a 0. And if the end is brighter than the beginning, it assigns it a 1. So you might have 256 little sticks. And for every stick, you compare the pixels at either end of the stick, and you get either a 0 or a 1, and out comes a 256-bit binary descriptor. Okay? It turns out these descriptors are extremely powerful. They're very expressive. And now they're also rotation invariant because of the previous slide, right, for what we learned on slide 30. So what you get out of that is a binary string, and these binary strings are extremely amenable to comparison, right? If I want to know if this particular feature with this descriptor matches this other one, all I have to do is just count the number of different bits in that string, right? Which I can often do on an Intel architecture machine. I believe I can do that in a single cycle for a 256-bit object, right? So very, very powerful tool. This is mostly for completeness, but also just to kind of beat the point home so that you'll wake up with some nightmares about it, but it'll stick with you. So this is the interface. This is the orb interface. Again, it's derived from this feature 2D. Again, it has this static member that is the create function that lets you create a pointer to an object of that kind. And then there's the usual list of things, all with very perfectly usable default values, which you can largely just stick with. Some of these things, the ones that you might consider tweaking, well, obviously a number of features you might tweak. The scale factor, you can, as long as it's bigger than 0, it's basically just telling you how many different scales to search, right? So I guess I kind of glossed over that, but the orb feature also has a size in the same manner as the SIF feature does, right? So that ring that was inherited from FAST is going to be applied to different scales, like an octave scale, pyramid scale of the images, so that you can then find the particular size, and then you can just tell it what you want that scaling ratio to be and the total number of pyramid layers to use. Again, this is the kind of number that, unless you're a real pro, so there's 3 kind of people. There's the kind of person who's never going to change that number, Okay? Then the kind of person who's going to get their thing working, then they're going to kind of prognosticate that number a little bit to see if they can improve it without really understanding, but they'll just try a couple things to see if it helps. That's like almost everybody in the real world. And then there's people who really think hard and have some really good reason to set that to some other number. And those people are like 1 in 1,000, probably, okay? But a little bit of toying with this number when you're very close to the end of your production process can be useful. Because you might say, you know, I had 8 levels here, but what if I drop that down to 4 levels? You know, it might save me 10% in performance. You know, does it really drop the quality in my application? Maybe it doesn't, right? So sometimes you can cheat a little and save yourself some, or you know, space out the levels a little in the scale factor or something like that. Okay. So let's talk about key point association, right? That was the question was asked. So how do I match them? So there's another tool for this that's built into OpenCV, and it's this tool called a descriptor matcher. So no surprise there. But what the descriptor matcher does is there's many kinds of descriptor matchers. I'll talk about that in a minute. But descriptor matchers basically solve the problem of, you know, is this key point like some other key point? But in practice, there's a lot of different ways you might try to do that. So the descriptor matcher tries to accommodate the different contexts. The 2 big context families are, there's the situation where you have one key point, and then you have a whole pile of sort of known stuff. And you're saying, is this like anything in that pile? Right? So imagine the situation where you have a grocery store chain, okay, and I'm describing a real product, by the way. These people actually exist, or they did. Their idea was people would sneak out of the grocery store by putting like dog food or whatever like at the bottom of their grocery cart, and then they would ring up all this stuff on top, and then they would go out without having paid for the dog food or whatever is in that lower level, okay? So their idea was they could produce a computer vision-based solution with a small camera that was kind of, you know, ankle high, and that would look at the cart and determine if there was something in the cart that, you know, wasn't rung up, like a dog food or whatever thing, right? So how would that work in OpenCV? Now, that product actually exists. It's called LaneHawk, I think. I don't know if it's still for sale, but years ago they licensed SIFT to make that product. And you would think, well, how did that work? Just go through it in your head. Well, okay, so there's, let's say, 1,000 known items of concern, things that are sort of big enough or fit flat enough to fit down there, and they often get stolen. You know, whatever, you know, Safeway knows that there's 1,000 things that might get stolen in that manner, right? So they say, oh, okay, what do those things look like? So you look at each one and you extract a bunch of key points from it. And you're like, this one's Alpo 30-pound bag, and here's 20 key points that are often found on such Alpo bag. And then here's a, I don't know what, you know, I mean, here's a flat of Diet Coke, and here's key points associated with that. Now remember that class ID and the key point? Yeah, 0 is for Alpo, 1 is for Diet Coke, and so on, right? So now you have this giant pile of key points, which you want to somehow like load into memory, right? And then you want to pull out one key point, or, you know, 2 or 3 that you found, and say, hey, is this key point, you know, does this look like anything you've seen before, right? And you'd like the computer to say, oh, that key point, yeah, those are found on Alpo bags. That one has ID 0. Right? And then, you know, if it says that's like Alpo and that one's Diet Coke and that one is whatever else, you know, then you're probably going to say, well, there's nothing down there, right? It's just noise. But if you get like 10 hits off of that all say Diet Coke, then you're going to say there's probably a flat of Diet Coke down there, right? So that situation is the situation, I would just call it, this is an object recognition type environment. And so you often find yourself with what people call a query descriptor, a single query descriptor, and a huge library. So you'd like to throw your query descriptor at your huge library and say, tell me if there's anything like this in there. The other really common context is I have 2 big lists of things. So for example, I have all of the key points I computed on one frame of video, and now I have all the key points I compute on the next frame of video. And what I'd like to do is, you know, load the first set into the matcher engine, and then just give it the entire second set and say, hey, do you see any matches here, right? And that's similar, that's how the Lucas-Canati algorithm, which we didn't actually talk about its interface, but the Lucas-Canati algorithm implementation of OpenCV does exactly that. It just says, okay, let's see. So, you know, the first one in the original set matches the 18th one in the new set. And the second one in the original set, I didn't find that one at all. And the third one matches the 13th one in the new set, and so on, right? So that's a very common case. So I'll show you that the descriptor matcher provides an interface for both of those 2 kind of things. So the most basic thing to do with the descriptor matcher is I create it using the ubiquitous create method, right? You'll notice there's this string here called descriptor matcher type. One subtlety here is the descriptor matcher doesn't quite work the way that feature 2D works. There aren't derived classes that implement different descriptor matchers. I just tell it, when I call the create method, I use a certain string and tell it what kind of descriptor matcher I want, okay? You can do that because in the case of descriptor matchers, they all have otherwise the same interface exactly. Whereas with the feature 2D case, each one had to have a different create method because they all took different arguments to parameterize them. Descriptor matchers don't have parameterizations as such. Then there's this thing, say add. What add does, it lets me just add a bunch of descriptors to things that I already have. Okay, so I just put them into this. When I create the descriptor matcher, since it's a function object, it has its own memory space. So I can call add and I can just load a bunch more junk into it. Right? And anytime I want, I can call add and add more junk. When I call train, what train does, it kind of digests all the junk I added. So like if you're thinking, what does that really mean in practice? It might mean that I gave it 4,000 SIFT features, which all exist in 128 dimensions. And when I call train, it's going to go build like a KD tree to sort those objects so that it has some hope of finding things in less than forever amount of time. So then I have this match call. And in the case of match, I give it my query descriptors. And then it's going to return the matches. And the matches are in this dmatch object. I won't really get into it, but a dmatch object's like, it's got room for like this thing matched that thing. You know, it's a very simple object. And then I can give it a mask and say, well, don't concern yourself with this particular set of things. But in general, I give it the query descriptors. Notice I don't give it the other ones, because the ones, the so-called train descriptors, they went in with the add function. So the normal structure is build the object, add the junk. There's a clear function, which I didn't put here, but that lets you throw away junk if you want. But you add junk, you train it, then you call match and give it your query descriptors. Now, this is just going to tell you if there are exact matches. Did I find exactly the thing you just asked for? Usually you don't want that. Usually you want something a little more sophisticated. So here, KNN match lets me say, k nearest neighbors, I'm going to give you some value of k, where I'm basically saying, I want the 3 best matches to this particular thing. Okay? Actually, in practice, what you almost always do is set k equal to 2. Because what you almost always are doing is looking at the quality of one match relative to the quality of the other match. And if the 2 matches are about equally good, then they're not matches at all, right? You'd like to see that if you're looking at 128 dimensions, right? It's a big universe. It's hard to wrap your mind around that. But in 28 dimensions, everything is really far away, except for things that are for sure right next to you, right? So if you wander into a 28-dimensional room and you're looking for one of your friends and be like, hey, you know, you sort of reach out and bump into someone with your hand, like they're probably like intended to be right next to you, right? Like it's very easy to get very far away in 128 dimensions. But the problem is it's hard to know how the scale of that, like how far is right for being close. And what you usually do is you compare it to the next closest thing. Right? And in 128 dimensions, you know, a person who isn't 3 feet from you is probably a mile from you, right? Because you think about how that, you know, add up all those squares, right? So lot of dimensions, a lot of ways to get far away. So usually you compare the nearest neighbor to the next nearest neighbor. Sometimes people look for more, but that's a really common trick. With the radius match, this is sort of working a little differently. If you have some sense of how close things should be, you say just give me everything that is within X distance in whatever dimensional space that I'm in, okay? And depending on the type of problem, this can be more appropriate or this can be more appropriate, but you actually tend to use these. Then also these are the interfaces for matching lists, so you use these more when you're doing things like tracking and stuff like that. And you'll notice the input array, when you call match, you give it the query descriptors and the train descriptors in a single go, because you know they're sort of more symmetric, right? You don't really do this whole load train reference thing. But the train system, if you add and train, that's extremely efficient when I have one monster database and one small group of queries. But here, when they're about the same size, then it's better. You may as well just do it in a single call. And similarly, there's a KNN and radius match for these type of matches as well. So there's a lot of different kind of matchers. I'm not going to dig into all of them, but basically there's just 2 things you need to know. Okay? There's brute force matching. And brute force match is like, it's going to try to find the best answer always, and it's going to do it by a linear time search on all the things in the reference database, right? Brute force matching is it's great for debugging. It's great for like really knowing what's going on. It kind of blows for performance. You do not tend to see brute force matching in production code, but it's often used. To have the brute force matcher at your disposal is a great way to verify that the more tricky matching techniques are sort of behaving as advertised. This flan-based, I should have put these in quotes, but flan-based and flan-based and brute force, those are the strings that you would actually give the create method, right? The flan is a library. Some of you may have come across it, fast approximate nearest neighbor. It's an existing library that's not itself part of OpenCV, though there is an implementation that's bundled with OpenCV. And flan is what you tend to use for production stuff. So if you want to find your nearest neighbor in 128 dimensions, there are many, many tricks to doing that. And those tricks are implemented inside of flan. So OpenCV just creates an interface to flan. Again, in practice, a lot of these things you don't really have to know in detail. You just have to know what to do, and it will probably work. And then you can worry about the details, usually when you're trying to get more performance. But in general, brute force is what you do when you want to be sure that the rest of your code works, right? And then flan is what you do when you want to not take forever. So let me talk a little bit about applications. This is another one of those little breakpoints. Questions? Stop. Okay, no questions right now. So the applications, I'm just going to briefly kind of flick through. We're mostly at the end, but I want to talk a little bit about just some of the ways these things are used. And of course, I've been doing it all along, but let me just throw some specifics out for you. So object recognition. This is the problem for which SIFT was originally created. There's a cereal box here, right? It's some Crunchies or something. And here's a big pile of cereal boxes. And the question is, can I find, is this cereal box present or is it not, right? And you can see that all these red circles, these are key points, these are like little SIFT key points. And because the thing is orientable, the fact that this is a little bit, this is rotated a bit doesn't matter. And the fact that SIFT is reasonably robust to very small affine transforms, it doesn't matter. This thing's a little bit rotated out of the plane of reference relative to the canonical. And so, it doesn't find every key point here on this or every key point here on that, but it certainly finds plenty, right? What, I don't know, 20 or 30 key points are matched here. And that's more than enough to be very confident. The odds of this happening at random are, 0, right? So object recognition is is an environment in which SIFT type key points are extremely powerful. People use in the modern era, of course, a lot's happened since key points, and like deep learning is very important. Everybody thinks deep learning is great for object recognition and so on. Deep learning is really powerful class-based object recognition, right? So if you want to find something that's a member of a class, like, is this a bottle? Is it a boat? These kind of methods are not powerful for that at all, right? Because they don't have that kind of generalizability. A boat, from the point of view of key points, is a collection of key points. Some other boat has not one key point in common with that first boat, right? And every attempt to make that kind of generalization either failed or was part of the progression that produced deep learning. Okay, I had a bunch more slides that I cut out because I got too long on how deep learning came out of all this, but maybe another time. So, but when you have a rigid object, a known object, not a class object, but a specific thing, a box of Cheerios, then these kind of methods are extremely powerful. And deep learning methods are actually not that powerful. Deep learning methods are not so good at telling, Cheerios from, I don't know what, some other cereal, right? Frosted Flakes. I'm not saying they can't, but it's a very inefficient way to solve this problem. And you'll waste a lot of time gathering data, training a huge network, burn enormous amounts of compute power running that network to do something you could have done, on a cell phone with like 20 minutes of coding. Yeah.
I think Google actually had a demo at the CloudNext. It said chocolate recognition. Is this, is this particular kind of chocolate versus that versus that? So I guess it can be made to work, just not as efficient.
Well, right, and that's what I was trying to leave you with. I mean, deep learning techniques are very, very powerful, but the amount of human effort that goes into training them and the amount of compute effort that goes into executing them, if you're trying to solve a problem that has this much structure, it's not a good idea to try to solve it with that much plasticity, right? So, building a building out of clay would be very slow because you have to shape every last thing. You can go to Home Depot and just buy a 2x4, it's already shaped like a 2x4, you know what I mean? Like, if you sort of do it the way it's supposed to be done, it can be very efficient. With rigid objects, if the object is deformable, depends on the way it deforms. If it's soft, it's probably a very poor choice to use key point techniques. But if it has, articulated deformations, it may be fine, like a robot arm or something. I mean, you'll just find the different pieces in different places. But the deformation shouldn't destroy the key points, right? Oops, what did I do? Oh, okay. So place recognition kind of follows naturally from object recognition, right? I mean, in some sense, places are sort of big objects. Some kinds of place recognition, it's really obvious, like it's just a big building, which is sort of like a big box of Cheerios. But in other cases, it's a little less obvious, where you're looking at kind of a cityscape or a more complex structure, and it will be a collection of different subcomponents that contribute, not just one object. But in many cases, this is very powerful. These kind of techniques are extremely powerful in, for example, augmented reality, right? An entire company, what was this company? Applebot, it's a German company. The entire company was built on key point recognition-based augmented reality. You can back out not just what's there, but the pose of some object. I'll talk about pose construction in a moment. And based on that, you can, put augmented content on top of an environment which you understand. So pose estimation is just another, yet more sophisticated evolution of that thinking. Not only am I recognizing that this particular thing, which I think is an F-22, is in a particular place, I recognize that it's there. Yes, this is a picture of a F-22 or whatever. But also, if I have some knowledge about the structure of this thing, if I already have a 3D model of it, then I can do a solving, and I can say, well, okay, I found these points, in projective space at these coordinates. So where's the airplane, right? And I should be able to figure out how far away it is, and obviously I have to know the camera parameters, but I know how far away it is and what its orientation is, and so on. All that from the key point library. So this can be a very powerful technique, and it allows me to, again, I can do it with, if I think in terms of an object, kind of an outside-in sort of mindset, I can calculate the pose of the object. But if I think in terms of a terrain environment, kind of an inside-out point of view, then I can figure out more relevantly where I am relative to the landscape, right? And then the last, probably most sophisticated case where these points features are used is very important, is simultaneous location and mapping, what people call SLAM, right? And in essence, building a map is just a matter of doing this inside-out pose calculation, one frame at a time, right? So as my robot, like here they have a little robot. It's like a Roomba with a laptop on top of it. I don't know where they got this, but it's pretty cool. And interesting, they're running this window manager called Terminator here, right? So maybe that's where they're headed with this little robot. But this robot is, moving around, and it's finding key points on a frame-by-frame basis, right? And it's going to move, one frame, right, a tiny bit of distance, and then try to compute, well, where have I gone? And then where have I gone, and move itself around. Now, that will do two things, actually. In the short term, it will allow the robot to add up differential guesses about its pose change. But the problem is it's kind of a dead reckoning thing that in net will cause a lot of accumulation of errors. But it can also note how these key points respond in response to its motion, which will allow it to model a physical constellation of where those key points really are. And because that produces a kind of feedback, it can actually sort of lock in, as it scans or goes around a loop or whatever, it can reason about what's the best possible explanation for all that it has seen around that loop. And this is kind of, I don't know if this is a great image, but I found it on the internet. This is an image where somebody's robot is cruising along. Each of these little blue things is a frustum representing the view of the camera. And then the sort of cloud, these are the key points that's been accumulated by this device as it moves along. So if it goes around a hallway and comes back and it sees a bunch of key points it's seen before, you'll say, aha, I know where I am, I'm back where I started. Depending on the sophistication of the SLAM algorithm, it will often go back and do a re-reasoning about that entire loop. It's called a loop closure in the SLAM world, to try to, because there'll be some error in its dead reckoned position relative to where it now knows that it is based on the key points it can see. And so it will ask itself, well, how must I have erred along the way? And then go recorrect all the observations it made along that path. That's a very common thing. We will obviously get into SLAM. If I were to do a lecture like this on SLAM, it would be like 8 hours long and we'd cover almost none of it. But I will sort of leave you at this point with the idea that this SLAM problem is really fundamentally a key point problem for most of its implementations. Now, there are other ways to do SLAM. If you're familiar with like Google Tango, then in the Tango case, you have a depth sensor, so you're really bringing in three-dimensional structure. And so there are ways to do SLAM that accumulate three-dimensional structure as well. But I'll tell you, if you bust those algorithms open, I mean, I can't bust that particular one open, so I'm a little bit talking out of my hat where Tango is concerned. But in general, if you bust open those algorithms, what you're going to find is those depth fields get turned into sort of depth key points that are like descriptors of shape. And then those are used for tracking and it ends up being the same. Okay, so summary and conclusions. This is pretty much the end. So, key points are those tiny bits of an image that carry a lot of information, okay? Both about the whole image and about themselves. Each key point is very recognizable. There are many kinds of key points. Some are fast to find, some have more representational power, some are easier to compare to one another. You choose key points based on the problem at hand. The reason that this whole zoo of key points exists is because every new key point is obviously better for some problem, which is the problem that the person publishing that paper was interested in. And so they always get their paper published, but then when you go try to solve the old problems with the new key point, you often discover that it's not any better or even worse. Or it does equally well but costs more compute or something like that. So this zoo of key points stays around because in practice, when you build production code, you often find that one key point type is substantially superior for that particular context, somehow taking advantage of particulars of whatever it is you're trying to do. So for that reason, we often experiment, and that's why the Feature 2D interface in OpenCV is built the way that it is, to really facilitate that kind of experimentation. Even at runtime, you can swap them around, right? And just the last thought, which is the basis of those last few slides, because key points summarize an image in such a powerful way, you can use them to recognize objects in the scene or places you've been. You can use them to calculate the pose of objects, or you can use them to calculate your own pose relative to known scenes, or you can kind of combine those in a loop and turn that into a simultaneous location and mapping implementation, where you can build a map and figure out how you move through some terrain as you might in a robotic environment. Okay, that's it. Yeah, questions?
The way set up now is monochrome. Are there any, when you go to color, are there distinctive differences, or is it all just the same color?
That's an interesting question. And it's true that everything I've talked about so far, every one of these images I mentioned is an intensity image. And people have experimented a lot with, like, is it useful to add color in some way? And if so, how would you do it? Color is kind of hated by computer vision people because color is such an unstable construct, right? Like the color of an object has so much to do with the lighting and so on that people tend to avoid things that make heavy use of color, or at least they used to. Because a lot of times the color just was introduced a vector for more variability than you wanted. Human eye is very good at kind of correcting for that. So you look at some green object, it looks equally green to you, even if the light temperature changes or whatever. But in fact, to the computer, its RGB value is moved all over the place. What people found in practice is that pretty much every attempt to produce key points that use color failed, okay? Or at least produced nothing of any real value. However, in the era of deep learning, I mentioned earlier, maybe I'll talk for a second on the deep learning idea or how this connects to deep learning. What people started doing just before deep learning, what was everybody doing in computer vision in 2010 or whatever? And basically, everybody had decided that the perfect learning instrument was the support vector machine. It was sort of used to solve all learning problems. And when I wanted to recognize something, what people would do is they would take a sort of large region, some kind of a window. I mean, let's say I'm searching for pedestrians or something. I'd take some window, and in that window, I'd calculate like a descriptor for the whole window, as if the window itself was kind of a key point or a feature. And I'd do things kind of like these orientable energy histograms and stuff that you see in the SIFT feature, or I'd combine it with this or that, or texture features, or color, or whatever, and I'd just sort of calculate that for this window, and I'd throw it all into a big support vector machine, and I'd just classify it, and I'd say, this either is or isn't, say, a pedestrian. I'm basically summarizing Dalal and Trigg's pedestrian detector for those of you experts. And that's just what everybody did. And what people realized is you could just throw more and more and more junk into that feature. Because the computer's got more and more powerful. I have 5,000 dimensional feature, and I just throw it in. And now I have like a pedestrian feature or something like that, right? And this was sort of working, but it was also sort of getting silly. And so nobody quite knew what to do. Now, what was happening in parallel with that is people who were thinking about deep learning's precursor topics, okay, they were very interested in, can you learn these features, right? Because what's happening is a bunch of guys are sitting around, in a lab, around a table, right, arguing about what the super best next feature is, and then they go implement it, and then, somebody get another PhD. But at some point, the number of features was sort of, the number of key points and feature descriptors and such was sort of heading to infinity, and the return on doing so was sort of asymptotically approaching zero, right? So at some point, people started to say, well, is there some way to just learn these features, right? Because we have a classifier at the top. Once we've handcrafted these features, we throw them into some learning architecture anyway. So can we just produce a learning architecture that will learn the features, right? And that's sort of how things began. And then deep learning is really just a connecting of learning the features at the same time with the same learning algorithm as you learn the classification, right? And that's how deep learning got deep, right? Because one problem got stacked on top of another problem and solved together. And it turns out that neural networks are a very effective way to create this kind of stackability and simultaneous training. So that's sort of where deep learning came from. So when getting back to the issue of color, which is how it got onto the deep learning thing, deep learning algorithms learned that there were sort of right and wrong ways to use color. So if you go look at how just about any sort of deep learning based object detector classifier, AlexNet, VGG, pick your favorite up to the modern era, look at how they work, they pretty much always learn the same thing. They learn that the most basic features in the world are edges of two kinds, what you might call like symmetric and asymmetric edges, or even and odd Gabor filters, or whatever your favorite language is, but sort of white turns to black, or white turns to black and then back to white again, right? Lines versus edges. And then it learns color blobs are very useful. So a blue blob or a green blob, or sometimes they'll get combined and you'll have sort of like a Gabor filter that's like a blue blob with an orange blob on the other side. And that detects anything created by like Michael Bay, right? So there's sort of this kind of, that was funny, somebody laugh at that, please. That's sort of the blue-orange filter thing, Transformers, no. Okay, so the idea is that those algorithms, they learned very quickly that there's just a few special places you use color, and then you pretty much throw it away. But it is sometimes very important, right? Detecting plants or whatever. Yeah.
I want to know which is the main growth of OpenCV against MATLAB.
The main what?
Growth.
So, MATLAB, well, it's a pretty continuous arc because programming things in MATLAB is rather similar to programming OpenCV in Python, right? And I know people who consider these totally interchangeable activities. Others are partisans one way or another. In general, MATLAB has many of the advantages of Python, and maybe to an even more extreme form. It's very easy to kind of throw things together and explore and experiment, and the environment's very friendly for that. OpenCV really originally came from a C++ type implementation, really intended for producible production and deployable code. So that was kind of where they began. But I think over the years, the level of arcing towards one another has been relatively high. And I think if you like MATLAB sort of way of doing things and you just don't like paying for MATLAB, you can pretty much just go to like OpenCV bindings in IPython, and you're going to get a very similar daily experience. Some combination with matplotlib and IPython notebook. But it's pretty much the same stuff, right? The MATLAB computer vision libraries choose to implement pretty much the same set of capabilities as you see in OpenCV. But OpenCV is the right way to go for production code. OpenCV provides a lot of implementations that are sensitive to various kinds of hardware optimizations and things like that. MATLAB is not great for, say, deploying to Android. So I think if you're a researcher or scientist, MATLAB or the more kind of plastic ways of interacting with OpenCV are probably equally good. If you're building production code, I think you might still choose to explore in MATLAB, but by the time you build the production code, you'll probably do that with OpenCV. Yeah?
Our researcher is using these kind of features as input for like deep neural networks, so they share reliable.
Yeah, not to my knowledge, and I don't think my own intuition would be that it wouldn't be so productive to do so. Because what deep learning has taught us is that given the freedom to do so, both the data and the expressive power, the deep network will really figure out what is the best thing to do. And over again, trying to take your human knowledge, like to do the obvious thing that you think would be a good idea, and take your human knowledge and try to guide the algorithm somehow, almost always results in lower performance. It's much more creative than you are if it's given enough data. Now, the different case occurs when you have very small amounts of data, right? If you want to use a deep learning type approach, when you have a small amount of data, then some method for guiding it to somehow absorb some of your biases might be better than nothing at all. Yes? Yeah.
Correct me if I'm wrong, but OpenCV was designed for classical CPU architecture. How does it connect nowadays to OpenCL?
Yeah, so OpenCV has, the implementation of OpenCV is since, I don't know, I can go way back and find this early slide, but OpenCV has underneath the hood implementations of most of the algorithms that are sensitive to all kind of hardware-centric optimizations. So, well, I mentioned here SSE, AVX, Neon, IPP, OpenCL, CUDA. I say and more. There's actually quite a few things on that list. So OpenCV is quite good at making use of those things. Some of them it does totally automatically, like IPP. If the libraries are on your machine and you have an Intel machine, it'll just do it. Some of them, like CUDA, you have to do a little more work to sort of tell it that's what you want. But in general, you can get very high performance using those kind of hardware features.
Core part doesn't have anything implemented for OpenCL and division?
What doesn't?
You have two parts of OpenCV, core part and
Oh, so it's tricky. Contrib, for the most part, I wouldn't expect the people who wrote things in Contrib to have gone to great lengths to optimize them at the level of, these kind of specialized hardware. But as a matter of practice, it's rarely necessary, because if you actually bust open the library and start digging around, well, the things that really benefit from these kind of operations are like convolutions and things like that, right? So nobody who writes something in Contrib is going to write their own convolution operator. They're going to use the one in core. So, things in Contrib in practice are a thin layer on top. Remember I mentioned that kind of ratcheting ideology. So everything in Contrib is really stacked on top of a huge, standing on the shoulders of giants, as it were, in all this work that's in core. So in a direct sense, Contrib things are probably relatively unlikely to have specialized optimizations other than where it's very clearly relevant. But in an indirect sense, most of the performance that you would want is probably going to come through references to core. But for example, in Contrib, there's this thing called TinyDNN, which is like a little deep network library that can load deep networks that you trained using other packages like TensorFlow or Caffe or whatever, right? And then you can train it using those other architectures, and then you can load it into TinyDNN and execute it inside of the kind of OpenCV headspace, if you like. And that obviously does have like CUDA acceleration built into it. And I think all the others too, Neon and so on. Another question? Or there's a question over here? Yeah.
So can you briefly talk about evolution of OpenCV under Willow Garage and IPCVs?
Sure. So OpenCV was originally an Intel project. It was an entirely internal project, right? And it was part of the same performance library group that produced IPP. And the idea there was to, like I said, just to produce something that would enable a class of algorithms that would make people want to buy faster computers. At some point, Intel sort of steered a bit away from that, And basically, they made it open source and they gave it to the community, and everybody involved got little plaques to hang on the wall of their cubes, and then, it was given zero budget. So that it wasn't quite clear, how it was going to move forward. But at that time, Gary Bradsky, who, as I said before, was the creator of OpenCV, he moved from Intel and went to Willow Garage. And so Willow Garage, which was very strongly advocating open source products and later produced ROS and so on, and also PCL, right, basically came out of Willow as well. I don't know if PCL, my own knowledge of PCL is a little weak. I don't know if it existed before Willow and like OpenCV just matured inside of Willow, or whether it actually originated there. But in any case, PCL, OpenCV, ROS, all those things got a tremendous amount of support from Willow Garage while Willow Garage was in existence. And so during that time, it grew up there. And then eventually Willow Garage sort of restructured, spun out a bunch of sub-entities, and then shut down as the parent entity. But by that time, OpenCV had gained a pretty strong level of support. And so the OpenCV Foundation continues today. OpenCV.org is the OpenCV group's sort of headquarters. And OpenCV continues to benefit from support from various companies that are large users. Now, if any of you are working at large companies that are not pitching in but are using OpenCV, it's definitely time to rattle your management's cage and get them to throw us a couple of bucks. Because it's not free by any means. OpenCV Library takes quite a bit of resources to maintain. One of the reasons it's been so successful is that there's a really professional group of people who sit at the absolute core of it, and those people do need to feed their families. So it's a blessing, but it also really means that we have to keep corporate support flowing into OpenCV to really maintain the quality. Having said that, there's a tremendous cloud. Witness these 4,100 patches. Tremendous cloud of people who are just fantastic developers contributing every day and helping the library either add completely new features or to find bugs and improve performance and so on. Yeah.
So far that the example you're using is mostly piece of object. How about facial recognition? How effective is OpenCV in those situations?
So OpenCV has any number of things, I think, in Contrib that are useful for face recognition, but key point methods are not good for face recognition. So, they're not horrible, but they're certainly nothing like state of the art. So in maybe the, early 2000s, people were still exploring how key point methods, even the corner of the eye, corner of the mouth, these things have a little bit of reliable structure to them, and you'd hope that maybe you could find a descriptor or something that would help catch them. But then what do you end up doing? What you end up doing is you end up finding certain special locations on the face and then building like a measurement vector that separates those things. How wide are the eyes, how far from here to the nose, or whatever these different standard measures are. And then what do you do? Well, that's a bunch of numbers, and you throw them in a support vector machine. And that's kind of like what people did. Facial recognition in the modern era is very highly specialized. The best facial recognition code in the world, to my knowledge, is Facebook's. Facebook's code is entirely built on deep learning and entirely built around something called a triplet network. So that's something you can look up. But in facial recognition, key point methods were never like a great way to solve that problem because face is too plastic, too sensitive to light, there's too many variables that make for non-constancy. And key points are really at their best when you deal with like rigid structures with highly reliable textures.
What's the name of the feature for Facebook?
Check out something called a triplet network. I think that's the correct. I'm on video saying that, so I hope I'm right. But I think that's the technique that's used in their paper that shows the most state-of-the-art public results. Who's doing, what's going on inside of Google or Microsoft or whatever, who can say. But that's a very powerful system. It works extremely well. All right, shall we wrap up for tonight?
All right.
Yeah, thank you, everybody.